Alright, so this is on least squares. This is video 1. This is probably going to be the theory video where we'll develop the theory, and then we'll do another video where we work out some examples. So, to give a little intro as to what's going on here, the introduction is sort of take a look at, suppose you had, say, a matrix equation you wanted to solve. So suppose you had a matrix A and a vector B. And you wish to solve something like AX equals B. This is a matrix equation. You could think about it as a linear system of equations. We'll look at both of these as we go along. But suppose there's no solution. Because we know such a system can have infinitely many solutions, no solutions, or one solution. So suppose there are no solutions. What can we do? So we could do nothing, or we could say, well, maybe there's a best solution, right? Like we cannot make AX equal to B, but can we get AX close to B? So we can't make AX equal to B. Can we make AX close to B? So let's rephrase this rigorously. So what we'll say is, can we find a specific X so that A times that specific X is closer to B than A times any other X? Can we find some specific, so the general notation here is X hat. So can we find some specific X hat so that AX hat is closer to B than AX for any other X? So even more specifically, that is the distance between AX hat and B is less than or equal to the distance between AX and B for all X. So that's our goal, right? Goal is to find such an X hat. So before we work this out, in other words, before we talk about how we can find such an X hat, because eventually we will, I want to sort of make a comment about what it means for a matrix equation to have a solution, right? Like a guy like this one right here, right? Other than the obvious, you know, you can plug in an X and you can get B. There's another way of looking at it. There's another way of looking at what it means for this thing to have a solution. So the question is, what does it mean? Or maybe, how could we rephrase it? For AX equals B to have a solution. So let's look at an example. The example will be enough to answer the question. So the matrix equation, say 1, 2, 0, 3, negative 1, 0, X equals 4, 5, 6. This has a solution if and only if there exists an x1 and an x2 such that I can plug those in like this and get 4, 5, 6. That's not surprising. I'm just sort of saying, hey, look, there are values I can plug in. But let's rewrite this. So we can rewrite this as 1x1. If we were doing matrix multiplication, we would do this. but I can still rewrite again. I can pull the x's out. And this is the same as saying that the matrix 4, 5, 6 is in the column space, or the vector 4, 5, 6 is in the column space of the matrix right here. That's A from the beginning, right? So remember the column space, the definition of this is just the span of the columns. So this literally means just this. That's a bit confusing, that's okay. As long as you can remember that the column space of a matrix is the span of the columns. In other words, it's all the linear combinations. And so in the line above it, here we're saying that 4, 5, 6 is a linear combination of the columns. So to summarize, just to make it clear, and then we'll go on to sort of how we can go about this. To say that Ax equals B has a solution means the same as saying B is in the column space of A. So in our particular example, B is not in the column space of A. We want to get something as close as possible. So let me clear the screen and we'll start to sort of take a look at a visual representation of how we could do this. All right, so let's rephrase the problem. And then when we rephrase it, we can draw a picture, and the picture will suggest a solution, and then we'll prove that the solution actually works. All right, so we have Ax equals B with no solution. So this means that B is not in the column space of A, because otherwise it would have a solution. And we want x hat. So Ax hat. Now Ax hat is in the column space. Is as close as possible to B. So here's a picture of the situation. So the column space is a vector space. So we'll think of it like a plane. It may not be a plane, but we're thinking of it as sort of some subspace. Here's the zero vector over here. We don't need to care about that. I'll just put it there. We've got, just to be clear, the blue plane, think of it as the column space of A. Again, need not be a plane. The picture just helps. And then we've got some vector. We'll think of it as a point, like the end of the vector if you like. You could anchor it at the origin, but it doesn't matter how we think about it. This is our B. This is clearly not in the column space of A. And what we want is something that is in the column space of A. Now remember, the column space of A is all the linear combinations of the column of A. It's all the A times something. And so we want something in this blue plane which is as close as possible to B. So the sort of the choice that gets suggested is this one right here. This point is in the column space of A and as close as possible to B. So can we use this? In other words, when I say can we use this, is can we find this point or vector and solve Ax equals this instead. Now, the way the picture is formulated, right, you can tell that I picked the point in the plane so that it was perpendicular because it gave a shortest distance, right? The as close as possible on the picture is this distance. So what this suggests is that we can take B we can project it onto the column space, like a perpendicular projection, and then we can solve AX equals that instead. Right? So this suggests, it's not a proof, but this picture suggests the following. We take B, project it onto column of A to get, just notationally, projection, column space of A, B. Then what we do is we solve AX hat equals projection on the column of A, B instead. Now, for what it's worth is this new equation will definitely have a solution. The reason is that the projection to the column space is in the column space. All right, so this is sort of a little redundant, but it's because this projection is by definition in the column space of A, which means I can solve AX hat equal to that, absolutely for sure. Now there may be many solutions, but don't worry about that right now. The point is that by projecting down into the column space of A, we can solve AX hat equals that new vector, and that will get us the result. Now this is not a proof, this is just a suggestion, right? So there are two things that have to happen now. One, we need to show that doing this will actually work. And then two, we need to find a shortcut, because this actual process of projection is ugly, and so we'd like an easier way to do it. All right, so there are two things to do. The first thing is to show that if we solve this thing, AX hat minus projection, or AX hat equals projection on the column space of A, B, we do get an X hat satisfying the original equation. In other words, the difference between AX hat and B is less than or equal to the distance between AX and B for all X. And the second thing we need to prove for sure, or not need to prove, the second thing we need to do, this is just for convenience sake, is find an easier way of getting this X hat. Find a slick way to solve for this X hat. So the reason is that the projection itself is a complicated process. So if we actually had to take B and project it onto the column space of A and then solve AX equals that thing, it would be messy. So if there's like a nice way around it, like a nice way we can get an answer without actually doing it, it would be even better. So I'm going to clear the screen, and then we're going to actually do it. In other words, we're going to do these two things. We're going to show that if we solve this new equation, we get the X we want. And then we're going to show how to solve this new equation in a really, really, really nice way. So 4 will say, how can we do these? How can we show these? Right, these two things. Let's look at A first. All right, first thing. Suppose somehow, magically, we solve this. What does that get us? So take a look at the following picture. The picture, we'll draw a few pictures in here that'll help us see what's going on. So let's step through the process of what we did, right? We had this B, which was not in the column space. We projected it down, right? So down here we got the projection onto the column space of A of B. Keeping in mind this blue plane is the column, or blue space, think, is the column space. And then we took this and we found this AX hat. However we did it. Suppose we've solved it. Now, let's take some other X hat, right? Pick any other X hat. oh sorry, any other x bar. A x bar is in the column space. So what that means is it's somewhere maybe over here. Now, because both of these, because both a x hat and a x bar are in the column space of A, so is the difference between them, right? So what we have is a x bar minus a x hat in the column space of A. Right? It's a subspace, so the difference is in there. Now, if we look at the difference a x hat minus b bar, this is perpendicular to the column space of A. This is the sort of the definition of this projection, all right, which we can see in the picture if you look up. All right, the vector that we're looking at is basically that dotted line, and that's perpendicular to the column space simply because we're taking a perpendicular projection. So keep that in mind and consider the following. Right, so consider that a x hat minus b, I'm just going to write an equation here, plus a x bar minus a x hat, that's the same as a x bar minus b. That's just from cancellation. The a x hats cancel and we rearrange. There's nothing special there. Right? Now here's the thing to pay attention to. These two right here and here, those are perpendicular. This is because this one is in the column space of A, and this one is perpendicular to the column space of A. So because of that, we can apply the Pythagorean theorem. The Pythagorean theorem will tell us the length of this vector squared plus the length of this vector squared equals the length of this vector. Now, if you look at this one right here, that's because you're squaring it. That's definitely greater than or equal to 0, which means if I delete it from the equation, what that tells us that this is less than or equal to this. And since they're both magnitudes, if we ignore the squares, what that tells us is I can drop the squares and get this as desired. So just to summarize, because this can all be a bit confusing, if the calculation or the process here is a bit confusing, the key thing to remember after all of this is that if we can solve this equation, then the x that we get is exactly the x that we want. In other words, just to be clear, let me summarize this in a sentence. So let's actually put this as a conclusion, just so it's really clear. So here's the big conclusion. This is just for part A. This is sort of the most theoretical of the two, is that solving this yields an x hat such that a x hat is as close as possible to b. Right? That's what we wanted at the very beginning, right? So the next question is like, okay, so how can we solve this in sort of an easier way than actually solving it? So let me clear the screen and then we'll talk through B. So let's say solving this. Easily. That's what we'd like to do, right? So first thing to remember is the fact about perpendicularity that we showed in the previous part. So we saw that ax hat minus b is perpendicular to the column space of A. So that was, again, I won't draw the full-fledged picture. This was b, this was ax hat. That is perpendicular to everything in the column space because it's a perpendicular projection. So remember, the column space is composed of things that look like ax for various x. So this statement right here, we can rewrite this as saying ax, a random thing in the column space, dotted with ax hat minus b, regular old dot product, will be 0 for all x. Because remember, the dot product being 0 gives you perpendicularity. So what we're saying is that ax hat minus b is perpendicular to every single thing in the column space. Now, the dot product can be rewritten as multiplication by a transpose. I'm going to keep writing this for all x. It'll vanish in a minute, but it's sort of critical to keep it in mind. Now, the transpose of a product is the product of the transposes in reverse order. And then if we rewrite this as a dot product, this can help us see what's going on. So what we've got here, we're basically close to done, is to take a look at this. What we've got here is that this thing right here is perpendicular to every single possible x. In other words, if you dot it with every single x, you get 0. The only vector that you can dot with everything and get 0 is the 0 vector. For example, if you dot it with itself and you get 0, its magnitude must be 0, and therefore it must be the 0 vector. So what we can say is that ax hat minus b must be the 0 vector, which means multiplying out atax hat minus atb is 0, which means that atax hat must be atb. So what this means is, after all is said and done, is instead of solving this original equation, what we do is we solve this new equation. Now, this is nice because it avoids us having to do a projection. Now, little note here. This will have a solution, absolutely. Because you might wonder, like, how do we know that this doesn't have a solution? How do we know that this does have a solution when the original one didn't? So this will have a solution because what we're doing is we're solving this, right? This original. We're just doing a different method of solving it. And this has a solution because the projection is in the column space. Like by definition, because this is in the column space of A. So if it's in the column space, you will get a solution, right? And so moreover, we can say one other thing. We can say that it will have a unique solution when the columns of A are linearly independent. Let me not forget the word unique. So this follows from basic linear algebra. When you have a matrix equation, if it has solutions, then the solutions are unique when the columns of the matrix are linearly independent, because then there's only one linear combination that gives you the result. So, again, just to summarize, I'll do a little summary here, and then I'll end the video, and then another video I'll do some examples. Actually, let me do this. Let me clear the screen, give a summary, because this is all sort of packed in here. So here's the summary. So if this guy has no solution, what we can do is we can instead find the solution to a TAX hat equals ATB. This will have a solution, and that solution will be unique if the columns of A are linearly independent. This solution, x hat, will get, just so we're clear, it will get AX hat as close as possible to B. Now, there's one last thing we can note. That if there's a unique solution, in other words, if the columns of A are independent, are linearly independent, then we can actually rewrite this thing. We can go even further. We can rewrite this as x hat equals, if I multiply both sides by the inverse to get the solution. And that makes things really, really sweet. So take a second to digest all that, especially the summary. And if the summary makes sense, in the second video, we'll just work through a couple of examples just to see exactly what's going on and how this is meaningful.